Greetings. We're going to talk today about inverse functions. So we have a function from r to r going in this direction. We're interested in the inverse function, which goes back in the opposite direction. And it's denoted f inverse. And it's supposed to be the function which gets you back where you started. So if x goes to f of x, when you apply f inverse to that, you want to get back x. It's the function which undoes f. That's the notion of an inverse function. So let's see what this means. In an example, suppose that, very simple example, f of x was 2x. Then what is f inverse of x? Well, it's 1/2 x. How do you undo multiplying by 2? It's multiplying by a half, and what you check is that f inverse is f inverse of f of x. Well, let's see, f of x is 2x. And what's f inverse of 2x? Well, f inverse of something is 1/2 times the something, and the 1/2 and the 2 cancel, and you get back x. That's just a very simple example. Okay, here's another example. Suppose f of x was x squared. How do you undo the square? Well, it's the square root. So I guess f inverse of x must be the square root of x. Is that really right? So let's check. If you compute f inverse f of x, what do you get? Well, f of x is x squared, and f inverse is the square root, so you're getting the square root of x squared. And is the square root of x squared equal to x? Sort of, but be careful. There's trouble here. What's the trouble? If x is -1, then f of x is -1 squared is 1, and f inverse of f of x is the square root of 1 is equal to 1, not -1. So the problem is, when you take the square root, you always get the positive square root. So somehow this doesn't work for negative numbers. So in fact, this isn't the inverse function. So let's look at this a little more carefully. Okay, let's be a little more careful. Another point that I glossed over is that square root of x is not defined if x is less than 0. So f inverse of x is equal to square root of x is a problem already. So to be more careful, let's say f inverse of x is the square root of the absolute value of x. Now, since the absolute value of x is greater than or equal to 0, that's okay, and we're taking the non-negative square root. So let's check. F inverse of f of x is the square root of absolute value of x squared, and that's the square root of the absolute value of x squared, and that's the absolute value of x, which is greater than or equal to 0. And let's check, is this correct? Is this the correct inverse function? Well, again, you have to check, is x equal to absolute value of x? Not necessarily. So that's a condition. X is equal to absolute value of x if x is greater than or equal to 0. So let's restrict the domain to the x's which are greater than or equal to 0 and define f inverse of x to be the square root of the absolute value of x. And I don't really need the absolute value here because it's positive. And then f inverse of f of x, again, sort of the same calculation, would be f inverse of x squared, and that's the square root of the absolute value of x squared. And again, you get the square root of the absolute value of x squared, and you get absolute value of x. And since x is greater than or equal to 0, this is equal to x. That's the only thing different from the previous slide. Since I limited the domain to the region where x is greater than or equal to 0, then this is the inverse function. So sometimes when the inverse function doesn't exist, you can fix that by looking at a smaller domain. Okay, let's draw a picture to see what's going on here. So here's the xy plane, and this is where we're going to graph our functions. And let's say you have some function which looks like this. That's the graph of f of x, y equals f of x. And what does this mean? Well, if you give me an x on the x-axis, right here, the way you compute f of x is you go up to the curve, and you hit the point on the curve, and then that's the point x f of x, and then you go to the left here to the y coordinate, and that y value is f of x. So you start on the x, you go to the curve, and then you go to the y. That gives you the function. So what's the inverse function? It's just turn around these arrows. So what does that mean? I'm going to start with this y and go this other direction. And this map is the inverse function, f inverse. And it's the thing that gives you back x. Okay, that all seems fine, but there is a pitfall here, and that's the following. So we've graphed this function, and remember, when you have a function, the graph of the function has a special property. The graph of any function satisfies the vertical line test. And that's the test that says if you draw any vertical line in the plane, it intersects the curve in at most one point. So if you have a general curve like this, you draw any vertical line, it only hits the curve in one point. And that's so that if you pick an x and you're looking for a point on the curve, there's exactly one that you get to. Okay, so why is this a problem? Well, when you're computing f of x, it's not. But when you compute the inverse, you're changing the roles of x and y. And so here, for example, you have x and you go up and you compute f of x and you go compute y. But now if you want to go backwards, you're going to start at y. And let's compute f inverse of y. Well, you start at y and you go along until you hit the curve, and you see that there's a problem. There's 2 points. You could choose this point or you could choose this other point. And depending which you choose, you get a different value for f inverse, or for the supposed f inverse. So the inverse is not well defined. The problem is that this curve, being the graph of a function, it satisfies the vertical line test, but in order to have an inverse, you have to switch the roles, and it has to satisfy the horizontal line test. And this example doesn't. So the inverse function might not exist. We've seen that already with the function x squared, after all. So let's look at that example of x squared from the point of view of these pictures. So here's the graph of the function f of x is equal to x squared, and it obviously satisfies the vertical line test, but it equally obviously fails the horizontal line test. On the other hand, if we saw that the way we could fix this is by restricting the domain, and what we did is we said we're only allowing x greater than 0, or greater than or equal to 0, and so the graph of the function is just this, and now it satisfies both the horizontal and vertical line tests, and so in this domain, this does have the square root, and that's the the inverse function, which is the square root of x as we computed before. The square root It's the square root of absolute value of x, but since x is positive, it's just the same thing as the square root of x. Okay, well, so let's suppose we have a function where the inverse function exists. Well, what's the graph of the inverse function? Let's look at an example. So let's do this example we've been doing. F of x is equal to x squared, and we're restricting to the region x greater than 0. And you see that this exchanging the roles of x and y, you draw this 45-degree line through the point 1, 1, and imagine reflecting the plane through the whole plane through this line. That takes the y-axis to the x-axis and the x-axis to the y-axis, and it takes this parabola to this blue line. And the black line is the graph of f of x, and the blue line is the graph of f inverse x. So when the inverse exists, the way you find the graph of it is you flip the plane about the 45-degree line. Okay, well, I want to say a few of these things a little more formally now, so just to have some concrete things put down. So we have a function f of x, and let's say it has some domain and it has some range, and I'll write the domain as x's and the range as y's. And both of these are subsets of R. They could be all of R or something less than that. And what does it mean to say f is invertible? F is invertible if there exists a function, which we denote f inverse, taking the range, the y's, to the x's, and which recovers x, which is to say such that f inverse of f of x is equal to x for all x's in the domain. So I said this already. I'm just repeating it and saying it all in one place a little more carefully. So that's what it means to say a function is invertible. Now, note there's a symmetry here. F inverse f of x is equal to x. If you interchange the order, you could ask that f of f inverse of y is equal to y, and it's easy to see that's automatic. If the first one works, then the second one does. So there's no difference, but it's the picture is symmetric in f and f inverse. Well, when does the inverse exist? So when can you find an f inverse with that property? Well, it's easy to see the following. F inverse exists if and only if the function f of x is 1 to 1. Okay? What does 1 to 1 mean? 1 to 1 means if f of x is equal to f of x prime, then x has to equal x prime. 1 to 1 means it never takes two different points to the same point. And this is just a mathematical non-picture way of saying the horizontal line test. It's exactly what 1 to 1 means. So let's look at a picture. If f of x is equal to x squared with the domain all of R, all x's in R, this is not 1 to 1 because, well, f of minus 1 and f of 1 are the same. They both have the same square. And that's just the horizontal line test failing. And on the other hand, if you restricted the domain to x being greater than or equal to 0, then it is 1 to 1. If two positive numbers have the same square, then they're the same. if x squared is equal to x prime squared, then x is equal to x prime or x is equal to minus x prime. But if they're both positive, then they have to be, the second case is ruled out, so they must be equal. And to draw the picture, again, this is just saying the horizontal line test fails because there are these two different x values with the same x squared, but it goes away if you restrict the domain. Okay, well, how does that help? How do you tell if a function is one-to-one? I mean, if you can graph it and look for horizontal lines, but if you're just given a function, it's not always so easy to tell, but often there's a very easy test to see whether a function is one-to-one and therefore has an inverse. Suppose the derivative of the function is positive for all x in the domain. So, well, what does that mean? That means it's increasing. And if you just draw the picture, it's clear that an increasing function satisfies the horizontal line test. That is to say, f inverse exists. And let's just draw a picture. Well, first, the opposite holds too. If f inverse is negative for all x, then the function is decreasing. And again, it has an inverse. And the picture is, well, just roughly, if you have a function which keeps going up, it's increasing, then it satisfies the horizontal line test. The only way that can fail is if it goes up and comes back down, more or less. Okay, so let's look at an example of that. Let's take this interesting function f of x is equal to x cubed. So the derivative of x cubed is 3x squared. And 3x squared is always greater than or equal to 0. Now, there's a little bit of the thing to worry about here. It's not strictly greater than 0, but let's not worry about that for the moment. Let's graph the function. And the graph looks like this. So you can see that f of x is clearly increasing. There's one, and it satisfies the horizontal line test. Now, the horizontal line through the origin, you got to be a little careful. That's an inflection point. And the derivative is 0 there, but it's not a problem because the derivative is only 0 at that one point. And so that doesn't cause a problem. The test is that the derivative is supposed to be strictly greater than 0, but it's allowed to be equal to 0 at a finite number of points. So, and looking at the picture, that's clear. This function is increasing, so x cubed does have an inverse for all x. Well, you know what it is. It's the cube root. And you can take the cube root of a negative number. In fact, the cube root of a negative number is negative. So let's draw the 45-degree line and reflect this graph about the 45-degree line, and you get something like this. The black is the function f of x, and the red is the function f inverse of x, which is to say the cube root of x. Okay, so if you have a function that's invertible, you get this inverse function, f inverse of x. And let's look at the derivative of f of x. What can you tell me? Suppose you know the derivative of f of x. What can you tell me about the derivative of f inverse? What's the derivative of the inverse function look like? Well, let's do a super simple example. If f of x is 10x, f inverse of x is 1/10 x. And let's see. So here's the 45-degree line. And this is the graph of my function, y equals 10x. And the inverse is what you get when you reflect it through this line. And that gives you the line 1/10 x. So it looks like it's changed the derivative from 10 to 1 over 10. So let's draw a picture and see if we can understand what that's about. So let's just look at the quadrant. Look at all the lines through the origin in the first quadrant. So here's the line with slope 10, and here's the line with slope 1/10. And this 45-degree line is the line with slope equal to 1. And you see that reflecting a line in the 45-degree line changes the slope to 1 over the slope. In particular, slope 0 goes to slope infinity. And so that's the key point here. And it's the following simple observation, that if you reflect the line in the 45-degree line, the slope m goes to slope 1 over m. That's what this reflection picture does. And that's going to tell us the relationship between the derivative of a function and the derivative of its inverse. So my guess is that the derivative of the inverse function is somehow 1 over the derivative of the original function. I'll put a question mark there. Is that true? Let's look. And what I did before was fine for straight lines, but what if you have a curve? So let's think about that a little bit. So suppose you have a function given by f of x, and f of a is equal to c, and you're going to reflect the graph around this line. It's going to change AC to CA. That's what this reflection operation does. It switches x and y. And so if you have a curve going through this point with some tangent line, well, when you reflect it, the tangent line is going to go to the line with slope 1 over that. So I'm just saying that this little argument that we made about straight lines, if you apply it to the tangent line to the function, it tells you that there's some relationship between, as I suggested. But there's one point you need to be careful of, which is the fact that A and C have changed. So notice that up here, the derivative is at A, and down here, the inverse derivative is at C. And so that leads us to the theorem, which is the following. Suppose you have a function which is invertible, and suppose you have a point A, and suppose f prime of A exists, and so that is to say it's finite, but let's also assume that it's not 0. Then the assertion is that the derivative of the inverse function at C is 1 over the derivative of the original function at A. And this whole slide was about pointing out the fact that A and C are playing a different role. C appears on one side of this equation and A on the other. Okay, so let's look at that a little more closely. First, let's do an example. Suppose I take f of x is equal to x cubed, and I take a is equal to 2, so f of a is equal to 8. So let's take c is equal to 8. And here's the picture, 2, 8, and 8, 2. So let's see, what is f prime of x? Well, it's 3x squared. So I compute f prime of a is 3 times 2 squared is 12. Okay. What is f inverse of x? Well, f inverse of x we know is the cube root of x, which is to say x to the 1/3. And so f inverse of x is, the derivative of it is 1/3 x to the minus 2/3. And so let's compute f inverse of c, which is 8. And, f inverse prime of c, which is 8. And that is to say f inverse prime of 8. And let's see, so that's 1/3, 8 to the minus 2/3. Okay, what on earth is 8 to the minus 2/3? So let's see, that's 1/3. Let's take it one step at a time. 8 to the 1/3 to the minus 2. And the 8 to the 1/3 is the cube root of 8, which is 2. So this is 2 to the minus 2, and that's 1/3, 1 over 2 squared. And indeed, you get 1/12. So that confirms this formula. And notice, and I plugged in 2 for the derivative. I plugged in a is 2, and c is equal to 8. And I found that the derivatives are reciprocals. Okay, let me state the theorem again, and I'm going to state it a little bit more carefully. Suppose you have a function such that f inverse exists, and I assume that f is continuous near a. Then the assertion is that the inverse function has a derivative which exists at c, and there's a formula for it, which is this. So this is almost exactly the statement I had on the previous slide, except I've been a little more careful about the statement. And I'm not going to worry about the existence of the inverse. That's pretty straightforward, but let's just check. So assuming that it exists, it's easy to find a formula for it just by this. The f inverse satisfies this identity, and just take the derivative of both sides, and that will give you the formula that you want. So let's just be careful. To take the derivative of this side, you need to use the chain rule. So that is to say, you have to compute f inverse prime at what point? Well, f of a, and then the second term is f prime of a, and that's equal to the derivative of the other side, which is 1. So, well, let's see, f of a is c, so this says f inverse prime of c times f prime of a is equal to 1. So there you have it. F inverse prime of c is 1 over f prime of a. And that really is the proof. With just a little bit of extra care, you can prove that the inverse exists and that this formula really is right. Okay, so let's do another example. Let's take f of x is equal to x to the 5th plus 1. I'm going to give you a 4-part problem. I'd like you to prove to me that the inverse exists for all x. Let's find an actual formula for it. Let's compute the derivative of the inverse at the point 33 using this explicit function. And finally, let's compute f inverse derivative at 33 using the theorem, the formula in the theorem. Okay? All right, so let's take these one at a time. How do you know that f inverse exists? Well, take the derivative. 5x to the 4th plus 0, that's greater than or equal to 0. And it's greater than 0 except at one point, which is 0. So just as in the previous example, that's fine. So you apply that test and it has an inverse. And the way you find the inverse for simple functions is you just write y is equal to x to the 5th plus 1 and solve it for y. So that is to say, solve it for x. x to the fifth is equal to y minus 1, so x is the fifth root. F inverse of x is the fifth root of x minus 1. So the inverse function is the fifth root, and I just changed x to y here because I want to think of it as the inverse function also as a function of x. Okay, so what is the derivative of the inverse function of x? Well, you just using the explicit formula, it's 1/5 x to the minus 4/5. And so if you evaluate that at the point 33, you get that the derivative of the inverse function at 33 is 1/5 32 to the minus 4/5. Sorry, this is 33 minus 1 is equal to 32. Okay. And, okay, what is 32 to the minus 4/5? Let's see, that's 32 to the 1/5 to the minus 4th. Just like previous couple slides ago. This is 1/5. The fifth root of 32 is 2, and 2 to the 4th is 16, and 2 to the minus 4th is 1 over 16, and so this number is 1 over 80. Okay, that's part C. Finally, let's look at part D. Let's compute this using the formula. So the formula says that f of x is x to the fifth plus 1. F inverse prime of 33 is 1 over f prime at the point A, such that f of a is equal to 33. Well, that's 2. That is to say, since f prime is 1 over 5 is 5x to the 4th, you get 1 over 5 times 2 to the 4th, and you get 1 over 80 again. All right, that's a good place to stop.